Hi, everybody. My name is Andrew Guo, and I would like to tell you about how to implement a fast, unbounded quantum fanout gate using parallel interactions. So the state of quantum computation as a field is in a very exciting place right now. Recently, Google has claimed to achieve a quantum computational advantage using their 53-qubit superconducting Sycamore processor, and its competitors are not too far behind. However, today's quantum computers face many hardware challenges. And in fact, I think I'm not too far off when I draw a comparison to Thomas Hobbes' famous quote about life outside of society, which is that it's nasty, brutish, and short. As a modern refresher, I would say that today's qubits without error correction are noisy, breakable, and short-lived, with the possible exception of trapped ions. But joking aside, I'd like to focus on this last point, which is that qubits these days are short-lived. More concretely, we like to say that modern qubits have short coherence times. So they lose their quantum magic very quickly. And therefore, our priority for NISQ-era practitioners is to implement quantum algorithms in as low depth as possible. So one possible way of addressing this problem is to parallelize the circuits, in particular to implement gates that act on different sets of qubits in parallel. And if you do this, you can get at best a factor n improvements in your circuit. Another possibility is to use multi-qubit gates. So these are gates that act on a constant fraction of the total number of qubits. And for example, these include gates such as the global Mortimer-Sorensen gate and trapped ions. And in the best case, these will give you a factor n improvement as well. So now either of these solutions are good, but we can do better. And it turns out there's actually a way to do better, and by combining these two ideas. And that's by taking your plain old vanilla parallelism and adding in multi-qubit gates to it to get an enhanced parallelism. So what do I mean by this? Well, so how do we define the standard parallelism? So standard vanilla parallelism says that gates acting on different qubits can be implemented in parallel. This enhanced parallelism allows you to say that commuting gates that act on the same qubits can be implemented in parallel. And so this enhanced parallelism uses the power of the unbounded quantum fanout gate. So the unbounded fanout is basically like a controlled NOT gate, but with many targets. And in particular, when we say it's unbounded, it means that the number of targets can be as large as the number of qubits you have in your system. So this is a cartoon of the controlled NOT gate, or a fan-out gate onto 3 targets. So how would you use fan-out to implement this enhanced parallelism? Well, let's take a toy example. So here you see we have a single qubit that's the control for 4 controlled unitary operations. And so these 4 operations cannot be parallelized in the standard fashion because they do not all act on disjoint sets of qubits. But they all commute with each other because their only overlap is in the control register. So one could use the trick if one had access to a number of ancilla qubits to implement control knots from the control line onto these ancillas, and then use all these qubits as the controls for parallel applications of the controlled unitaries onto the target qubits. And then finally, one must uncompute the ancillas at the end. So now this middle step can be done in constant depth. because these gates are non-overlapping. And furthermore, these gates in red, these control nuts, are actually just another way of implementing the fanout gate. And so you can implement a fanout quickly, then you can get a constant depth circuit. So now this is, a nice toy example, but what is truly, the extent of the power of this model? One can demonstrate this by using, as an example, the quantum Fourier transform, or QFT. So without the power of fanout, the time it takes to approximate the quantum Fourier transform is proportional to log n. This was shown by John Watrous and Richard Cleave. But with fanout, you can do the approximate QFT in constant depth. And this was shown by Peter Hoyler and Robert Spalek in 2005. And they also were able to show that you can implement certain arithmetic operations, such as modular exponentiation, in constant depth. And putting this together with a constant depth QFT allows you to implement Shor's famous factoring algorithm in constant depth as well, assuming some polynomial classical preprocessing. And so this is incredibly powerful, and I think demonstrates the incredible power of the fanout gate. However, there is a problem when it comes to implementing this gate. So in practical sense, there are limitations to how quickly you can implement this fanout gate due to restricted architectures leading to computational overheads. And for example, if you look at Google's Sycamore chip, can be represented as the following 2D grid of n qubits, and the time it takes to implement a gate that spans order n qubits will scale as the number of qubits, and which will be some polynomial of the total number of qubits. And so this will kill any potential speed up that you could achieve from these constant depth circuits due to the time it takes to implement this fanout. However, one could potentially achieve the speed up using a slightly different platform for qubits, specifically that of atomic and molecular systems that have long range or power law interactions. So what are these power law interactions? Well, they consist of pairwise interactions between all of your qubits that decay with a strength that is inversely proportional to some power of the distance between the qubits. So there's this power alpha. And these interactions are present in AMO systems. So in Rydberg atoms, you can have van der Waals or dipole-dipole interactions. You can have polar molecules with dipole interactions. And you can also have 1D trapped ion crystals with tunable power law interactions. All right, so that's it for the introduction. Now the outline for the rest of this talk. I'm going to first present a protocol for implementing a fast fanout gate using power law interactions. And then I will talk about one application of this protocol, which is proving the intractability of classically simulating power law systems. And finally, I will talk about our new technique for proving a circuit depth lower bound for the more restricted qubit architectures, such as this grid. All right, so without further ado, how do you implement a fast fanout gate? We first start with this subroutine, this entanglement generation subroutine, as I like to call it, which is as follows. If you are given an n-qubit system that starts in a product state of psi tensor product with all zeros, where psi is some superposition of 0 and 1 with coefficients a and b, then the task of broadcasting the state psi into a GHZ state is this operation here, where you take the single qubit superposition into this macroscopic superposition over the all zeros and all one string with the same coefficients present in the original state. So this task here can be viewed as an entanglement generation subroutine. And so it can be done using the following Hamiltonian that consists of two qubit interactions. So H is equal to the sum over pairs of qubits I and J of these pairwise terms. And these terms look like some coefficient that's potentially time dependent times the projector onto the one subspace tensor product with the X target on the qubit J. And these interactions have some coefficient that decays as a power law in the distance between the qubits. So if you stare at this for a little bit, you can see that Hij actually can implement this controlled NOT gate between I and J in time that is inversely proportional to the strength of the interaction. And so in this way, you can actually generate the GHZ state by using a cascaded set of these controlled NOT gates. So what do I mean by that? So you can look at the following picture. So if you have, you start with a set of controls. So these are qubits that are at some intermediate time already have already been acted on by a C0, and so have the same state as this original qubit. And then they are implementing these pairwise interactions onto the rest of the qubits in the lattice. So once one of the qubits that is being acted on by these controls finally rotates enough into the GHZ state, then it gets added to the control qubits and then starts acting as a control onto the rest of the qubits in the lattice. And then you can iterate this recursively and implement control knots in local regions around the controls until you finally cover the whole lattice. So this procedure allows you to do fan out. So the way you can see this is that if you have some data qubits, so if you want to implement the fan out from data qubit 1 to data qubits 2 through n, they might not necessarily be in the all zeros state, so you will need to use some ancilla qubits. So what you first do is you initialize the ancilla qubits in all zeros, and then you implement a control knot from the first data qubit to the first ancilla qubit. And then using the long range interactions or the entanglement generation subroutine, you can broadcast this state on ancilla register 1 to all of the other ancilla registers using this GHZ creation subroutine. And then once you've achieved this, then you can apply fan out onto the data registers by using these local controlled NOT gates from the ancilla to their respective data qubits. So that's how you do fan out using this broadcast subroutine. Now the time it takes in order to create this GHZ state can be shown to scale as follows. So there's some scaling of this time that depends on the strength of the power of these interactions relative to the dimension of your lattice. And in particular, one can observe that all interactions with alpha below 2D scale sublinearly in the system size. So polylog n for alpha between D and 2D. And so this actually applies to a broad range of interactions, such as dipole-dipole interactions in 2 or 3D, or van der Waals interactions in 3D. And they can implement this fan-out gate in time that is faster than any polynomial in N. So this is truly a fast fan-out gate. Okay, so now that I've shown how to implement the fast fan-out, I will talk briefly about one application of this protocol. Now, we all know that simulating quantum systems is hard, otherwise we wouldn't have a job. But still, it's not easy to prove that a particular quantum system has achieved some computational task that would otherwise be intractable on a classical computer. For example, Google in 2019 claimed to have demonstrated quantum computational advantage using their Sycamore processor. And what they did is that they performed a sequence of single and 2-qubit gates for up to 20 layers of circuit depth. And they claimed that sampling from the resulting state would take 10,000 years in order to simulate on a classical computer, as opposed to only taking 20 seconds to sample from on their device. However, there's been a lot of back and forth disputing this result, and successive classical algorithms have been developed that cut this 10,000 years number a lot shorter. And basically, the state of the assumption or this this proof of hardness is still in doubt because it relies on a very non-standard complexity assumption, i.e. that of where if you try to compute the output probabilities of random quantum circuits on a classical computer, you really can't do much better than just guessing randomly. So this assumption is pretty strong and not a very standard one that we can believe very easily. And furthermore, this task is very computationally expensive to check. So the confidence that you have on whether or not your circuit actually performed the correct thing you wanted it to is going to be hard to verify. Okay, so now that I've sufficiently cast doubt on Google's result, let me provide an alternative. So one way of potentially, having a more well-founded assumption on which to base your claims of computational advantage is that of sampling from the output state of a system evolving under a sufficiently strong power law interaction Hamiltonian. So specifically, that which is shown here with power law less than 2D. And if the system evolves for time that is polylogarithmic in n, then it will be as hard as factoring to sample from in the worst case. And so this argument proceeds by a reduction to factoring using the fast fan-out protocol. So since one can implement Shor's algorithm in time that is at most polylogarithmic in n, using these parallel interactions, then one can show that this is a way to demonstrate that sampling from this parallel system is as hard as factoring. So this this is a pretty well-established hardness assumption. It's generally believed that factoring is hard. It would be an easy to verify computation insofar as that you would be easy to check that you've outputted a non-trivial factor. And finally, this could be a potentially useful task for cryptography. Okay, so now let me move on to the final part of this talk, which is to prove our circuit depth lower bounds in restricted quantum architectures. So what are these circuit depth lower bounds good for? Well, primarily they're useful as benchmarks to show how close your quantum algorithms are to being optimal. But they are, in general, very challenging to prove and involve some sophisticated mathematical machinery, such as the polynomial or adversary methods and quantum query complexity. But our goal is a little bit more modest. So what we want to show is that certain multi-qubit unitaries require quote unquote deep circuits on restricted architectures, such as the 2D grid shown here. And in particular, we'd like to show rigorously that the time required to implement these unitary scales proportional to the diameter of the graph. Okay, so now previously, Dmitry Maslov showed in 2007 that for a specific circuit shown below that implements the quantum Fourier transform on n qubits and the 1D linear nearest neighbor architecture requires big omega of the number of qubits in circuit depth. So this result is what we shows what we want for the quantum Fourier transform, which is a multi-qubit unitary. However, one drawback of this is that this only applies for this very specific circuit that implements this quantum Fourier transform, and not for all possible ways of implementing the unitary associated with the QFT on this architecture. So what we set out to show is a more general result. So we show that there exists a lower bound proportional to the diameter of the graph, R, on any time evolution that can implement the QFT unitary or even approximate it on a nearest neighbor grid. So the main idea here is that the QFT unitary can spread operators and therefore obeys the Lieb-Robinson bound. And so what the Lieb-Robinson bound says is that if you have a system with local interactions, then the time it takes to spread an operator non-trivially over distance r is going to be lower bounded by r. And this lower bound holds for all implementations of the QFT and approximate QFT. And as a corollary, this also lower bounds the time it takes to implement the fanout gate, since the fanout can implement the quantum Fourier transform in constant depth. And so lower bound for the QFT is a lower bound for quantum fanout. Okay, so to conclude, I gave a protocol for implementing an unbounded quantum fanout gate using parallel interactions that enables the performance of the QFT and the Shor's algorithm using constant depth quantum circuits. As a corollary, this showed that simulating power law interactions on a quantum computer for a specific range of the power law exponents for time polylogarithmic and system size is as hard as factoring. And finally, we gave a lower bound on short range architectures being able to implement QFT and fanout, and our inability to do so in circuit depth that is shorter than some polynomial in the system size. So with that, I would like to say thank you to all of my collaborators and to you for your attention.